So the members of our project is Pophal, me, Anthony Garcia, and Alex Bugielski. We have a coach, Anthony Stefan. We're all from Florida Tech. We're doing problem C, and we're team 1005. So we will be explaining the problem clearly and concisely. We're going to apply some natural assumptions. We're going to show that the model followed these assumptions, and we're going to demonstrate that the model with some simulations that these assumptions are valid. We're going to conclude with the discussion at the end. So the problem gives us a division between people, at least two groups, and we seek to understand how the warnings and context moderation differ for the impacts on these groups and how this influences some movements on the population between groups. So we're going to assume certain things. We're going to say, oh, people change their opinions based on who are they connected to. Company A and B are going to influence these people. The biases have a preconceived state. We have some smooth transition between states, and these states have a certain idea, which in our case, we're going to choose from -1 and 1 because these are the representation of the values of A and B. We're going to assume other things like the companies do not change their state at all. The biases do not change their state at all, so they have a similar behavior to the companies. And a person can change their idea because of the biases. So first, we're going to have a certain structure for the vertices. It's going to be looking like an array. So we have company A and B, two companies, bias 1, 2, and 3. So 3 biases and people. In our case, we're going to simplify because we only want 2 companies, and the biases will be depending on the amount of companies. So it's going to be the extremes and some neutral points, and the amount of people are going to be there. So the function that represents the idea receives 2 inputs, which will be what the vertex is. So the company, bias, or people, and the time that which you are at. So it's going to be a real number, a positive real number, because time cannot be negative. So the idea will be between -1 and 1 because the company idea will be extremes. We're also going to define some other functions which will be used later, which is users, and we have an input of company, which will state everyone that is connected to that certain company. So we're saying the company's ideas and the biases are going to be fixed. So company A will have 1, company B will have -1, bias 1 will be extreme of A, so 1, bias 2 will be neutral of A and B, so 0. Bias 3 will be extreme of B, so it will be -1. And this function is differentiable and smooth.
So in this graph relationship, we need to describe the edges, the connections between vertices on the graph. So we do that with a function that's take 2 vertices and a time and outputs a non-negative real number, which describes the weight between them. We think of this as how they are connected. I weight my things and my friends highly, therefore they are strongly weighted to me. Now, this is the second vertex applying the first. It is non-symmetric. And we can also say that the weights between companies, biases, and everything else will be 0 always, because the companies and biases don't care about individual people. Now, to get a differential equation, we need to get an analog of calculus on graphs. And so we define a relation that 2 vertices are related if there's an edge from one to the other. In order, it's a directed edge. And so we get a partial along this directed edge is the difference of function values on them at that time. We collect a gradient by connecting all the partials which are connected by this edge. We write all our functions in one specific vector, that's like our system vector. And the time partial is applied component-wise. And we can also write the collection of gradients as kind of a total derivative. Now there are some dimension issues which we see next. If we look at the graph on the left and consider the gradient at x5, we see it has 5 components because there are 5 vertices it's connected to. But if we look at it from x1, there's only 1 component in the gradient. This error in dimensions would prevent us from multiplying matrices. So to remedy this, we fill all the entries with 0 if there's no edge, kind of an empty connection. Now, based on our assumptions on how we change with the people that we're connected to, we would expect it's kind of like a dot product represented with the connections and how we're weighted and the change, of course, in that partial. Writing this into a matrix form, we get a weight matrix, which we will define in a second, the total derivative matrix, and a vector of 1, which represents how everything relates that I'm connected to. This weight matrix appears sparse, but it depends on the number of people. The rows of zeros in this weight matrix represent the fact that the companies and biases don't care about people, and they receive no input, they remain fixed, as our assumptions are. The weights are non-symmetric, of course, but they also change with time, and modeling this is a little complicated. So to discretize this system, which we have to discretize it because the weights are too complicated to model, we can't model the strength of friendships over time. We apply the usual first order discretization with the previous step, time step, and derivative inside. Now, solving for this weight function, company A, we know, uses a warning. So we assume every user, xi, has a probability to accept or reject this warning. Now, depending on that, it issues a different value on a uniformly random variable, right? So the 0.01 is if they reject the warning, and that means they aren't siding with the company, but they still use the company. So there's still some connection. The 1 means they agree with the company, and they will not they will heed the warning, and 0 represents that they are not a user, so of course not related. Similarly, we define the weight with company B with a moderation team, right? So company B, the moderation team works on weekdays, takes weekends off. Our time runs in months, and so during weekends, the person is not strongly weighted with B because the moderation team isn't controlling what they see. All other times, so all other days during the week, they are very strongly connected at 1, and of course 0 when there's no connection.
So to test this out, we did 3 different simulations. Our first was the selective warning. Since A forces stochastic change, we can only observe a realization, but however, we still see the warnings are effective even for non-believers as displayed by the graph. Company B is going to be used for our second simulation, which is the moderation team, as an effective moderation team during the week outside of true believers. Also, B sees some disruptions, which are roughly around the weekends, as we had in our model, it's less used in the weekends. Our final test was a combination test with the assortment of users that are randomly chosen to use company A, B, both, or neither. This was completely randomly done, and we observed a polarization of the group as seen below. So some notes and limitations of our model. We noticed B, it was more consistent. However, A had the chance to poll non-believers. Our limitations included the following: a constant relationship with strengths between friends. We couldn't measure any change in friend groups or new friends. Stochastic nature makes it difficult to visualize. Our group was small at 10 people. Full analysis requires a larger friend group and a larger matrix to model more companies and friends. Companies have fixed beliefs. Values always change smoothly. And first order discretization error issues. So in conclusion, we developed a model on how leanings change with time in a group. We implemented this model with 2 moderation strategies and observed how people changed over time. We drew conclusions from this model about the different strategies. And we would like to thank our coach, Anthony Stefan, SIMIODE for providing us for this opportunity, and the judges at SCUDEM for taking the time to watch and review our presentation. Thank you.
Thank you.